All right, folks, thank you for showing up. Before we go any further, I want to make sure that you're the right audience because I don't want to waste anybody's time. If there's another session that might be a better one for you, I want to set that expectation now. So I'll be honest, you may be bored if you're pursuing a degree in AI, if you've already written a bunch of neural networks for yourself. If you came to this workshop hoping to see a whole bunch of code, or if you dream in Python, you might get bored today. However, if you're here at this hack because you're building simulations, you're maybe focused on a path with XR, AR, VR, or maybe neural networks just seem like this weird thing, this black box that doesn't make a lot of sense, then you're in the right place. It's also okay to dream in C#. I'm guilty of doing that from time to time. So, what I want to do today is to tell a story to kind of try to teach you about how we teach computers to understand the world, which is a big part of what we do in augmented reality and mixed reality. Okay, so this is me. I have been with Microsoft going on 15 years now, actually 15 and a half years. Been a wonderful career, but I've been doing HoloLens and mixed reality work now for about 6 years, which means that the first time that I wrote a HoloLens application, this is what I wrote it on. So that was a prototype device. That was what we were hacking on internally before we shipped the product. And since then, I've helped a lot of partners build applications that have been very successful in the platform. And like I said, neural networks were always kind of this black box thing that I didn't understand how they worked, but they were kind of in a different space. And that was okay to me because I was in Unity and I didn't care so much about them. But the more that I spent time in HoloLens, the more I realized how much of this space actually depends on neural networks. So you may have heard that HoloLens 1 had this chip called the holographic processing unit, and in HoloLens 2 we got HP 2.0, and that chip does a lot of things. It takes all of the feeds from the different cameras that are on the device, and it tracks you in space, figures out where you are in space. In HoloLens 2, we also added the ability to do hand tracking, articulated hands, so you could poke buttons, and that too was done with neural networks. And so that's when I really wanted to start figuring out and understanding how these things work, okay? So what is a neural network? I love this quote by our dear Senator Ted Stevens: "The internet is a series of tubes." I'm going to present to you today my case that a neural network is a series of tubes. And yes, I am going to oversimplify this concept, but I hope by the end of this, my goal is that you have enough knowledge and foundational understanding of a neural network that you could have an intelligent conversation with maybe somebody who's building neural networks, okay? So if you've ever read a paper, seen a website or a YouTube video that talks about a neural network, it usually starts with a diagram that looks something like this, right? So what is this thing? I'm going to take you step by step through what this thing is. And this is a representation of a very common type of neural network that we would call a classifier. It does one job. It does one job really well. It predicts whether something is a dog, a cat, or a giraffe. And that is the only thing it can do. Okay, so this is the first kind of important thing to understand about neural networks, is that they have a fixed set of tasks that they can accomplish. And this one will predict those three things. Now, on the left side of the graph, the input side of this graph, I've got a photo. And again, I'm oversimplifying here a lot, okay? I'm kind of taking all of the red pixels in this photo and grouping it into this bucket, and all the green pixels and grouping it here, and blue here. In the real world, I want you to understand that every single pixel within that photo is an input entry point into that neural network. Okay, so all the red value, green value, blue value for every single pixel is going into that network. Now, we do tend to start with smaller images, like you wouldn't give an 8K image to a neural network because that would just be a monstrous number of inputs to that network. So we tend to start with smaller networks. But as I go through this talk here, just imagine that all of the pixels from this input are coming in. So I said that I'm going to treat a neural network as a series of tubes. So let's imagine these pixels flowing through this graph as if it's water. Okay, in this picture, I've got yellow. I've got a lot of yellow in this picture, which is, of course, red and green pixels. So you see more red and more green flowing into this network, not so much blue. And then we hit this first set of nodes right here. And it's important to understand that a neural network is really just a graph. It's a graph with a bunch of gates in it that controls the information. And my little picture right here is not quite right because the nodes that I have in this graph are all organized. This is not how neural networks start. When you create a neural network from scratch, your neural network starts with all of these knobs here at random values. So it's just initialized with noise, which means that when you give it the very first image that it's never seen before, then the data flows through this network in a very random way, and you end up with a random guess at the end of the network. So in this case, we give it a picture of a dog and it guessed, I think it's a cat. Thumbs up. Hey, it tried, right? But the point is, the water has flowed through this graph. It has an input and it has to go somewhere at the end. It has to go to some prediction, and it's gone to a random prediction. Now, we know that this answer is wrong because we're human and we're really good at classifying stuff. So what we do, well, in our water analogy, I like to pretend that we put a cork in it. We say, no, bad neural network. It is not a cat and it is not a giraffe. Those are wrong answers, okay? And in my analogy here, my internet is unstable, I guess. In my analogy here, this causes that water to flow back through the network and be forced into predicting the right answer. Okay, now, I'm going to give you your first neural network term here. What I just did is what we call back propagation. This is where we go from the wrong answer and we try to start pushing the network over to the right answer, okay? I've said this is water and I've plugged the hole. Really what happens is a more complex mathematical algorithm that looks at each one of these little kind of nodes in the network to see how much they contributed to the error. So if one of these knobs contributed a lot to the wrong answer, that knob will get turned more. If this knob contributed just a tiny bit to the wrong answer, then it's only going to get tweaked a tiny amount. And that is how back propagation works. Okay, so we turn off the pixels, the network goes quiet. But the knobs are still set to particular orientation. The knobs are still set now with a propensity to predict dog. So I'm going to give it a new picture. This one is now a cat. It has more blue pixels, few green, very little red. And these pixels flow into the network, but because the network was previously tuned for dog, well, guess what happens? I mean, we still have some pixels that flow out these other outputs because it's a graph, they can go where water can still flow. But the network has been tuned to predict dog, which is, again, the wrong answer. So as we did before, we plug the two wrong answers. We do our back propagation. Same thing. We want to turn the knobs that contributed to the error the most, a lot. Turn the knobs that didn't contribute to the error a little bit. And now we have a network that is good at predicting those two images well. If we give it those two images again, it will predict the right answer. And we repeat this process over and over. We give it lots and lots of images. We give it lots and lots of answers. And these knobs turn, and we get to a network that can do a prediction. So at the end, we give it a different picture of the dog. And if we've given it enough training data, then hopefully the water flows through the network and we end up with a prediction of dog. Or we end up with a prediction of dog that is more dog than the other things, right? More the right answer than it is the wrong answer. So this is everything that we just talked about in this graph. I'm going to start kind of overlaying the neural network terms that we have here. When we talk about a neural network, these pixels on the left-hand side, that's our input layer. So this neural network takes pixels, and its output layer predicts a category of exactly 3 things, either dog, cat, or giraffe. Now, how good do you think this network is going to be at predicting a giraffe if we were to give it one? Very bad, because we've given it no examples of a giraffe. There might be a prediction of like 1 or 2%, but it's probably going to try to predict dog or cat because it's never seen a giraffe. And this is really, really important to understand, is that these networks are not like human intelligence. They don't have the ability to infer. They're not born with some carnal knowledge that pain is bad and food is good. They only can do what we've taught them to do from scratch. Okay, so where's my mouse? There we go. Oh, this box called hidden layers. Anybody know why we call those hidden layers? The way that it works is hidden. Yes. Oh, we humans never touch this layer. The programmers never do anything with this layer. It's that process of backpropagation, which itself is a program. It's the program programming itself. We don't see it. And for the longest time, we couldn't even like visualize what was going inside of this black box. We just knew it came up with the right answer. I'll show you in a little bit how this works. We're able to visualize these things now, and they're phenomenal to see. Okay, so this little knob that I've been talking about up to this point, that's your neuron. The gate that the water flows through is your neuron. And the knob, how much we turn the knob, that's what we call the weight. Okay, again, I'm oversimplifying a bit here. Really, in a neural network, what happens is you have a mathematical function called the activation function. And depending on how much that knob is turned, that knob will change how sensitive that neuron is, like how much data has to flow into it for it to be activated. And that knob will also change how much data flows out of it. So that weight changes a lot of how the network runs based on this function. But you can think of weights as those knobs that are in each node of the graph. Here are some other terms. So this whole time I've been saying bad neural network predicted that wrong because I know that's a dog. That's what we call a label. So when we have our training set of data that we're going to use to train the network, usually a human has gone through all of these photos and said dog, cat, giraffe, cow, whatever. They've pre-labeled them ahead of time. That's how we kind of check the neural network's homework to make sure they got the right answer. We already talked about the layers. We already talked about the neurons. The only one we hadn't seen before are these things that are the synapses. And when I show you a video later, there's a shocking number of synapses in a neural network. Every node in that network is connected to every other node in that network, or at least on the layers. There are a lot of them. And I'm getting back-to-back phone calls. Love that spam. All right, so want to show you a real-world example of this, one that you may have actually used up to this point. And to do that, I'm going to run an app on my phone. I have phone tethering turned on here, so what I'm actually running is an app on the phone here, so you can see yourselves. But I'm going to go in to my library and I'm going to pick these pictures of this goofy dog. This is a dog that is a friend of the family. And select all of those and hit OK. And these photos, hopefully my network is going well. All 3 of those pictures of that dog are going up to a cloud service that's doing a recognition on these 3 photos. And instead of predicting dog, cat, and giraffe, This network is trained to predict dog breeds. So on that output layer, there might be 50 or 100 outputs that represent each different type of dog breed. Now, all three of those pictures were of the same dog, and this network did a great job. It said, I'm 88%, almost 90% confident that this is a great Swiss mountain dog. It is, so it predicted it right. And all of the other guesses that it had were so low that it didn't even bother sharing them with me. But I can mess with this neural network after I close this app because it's going to show me an ad. So I'm going to do this again, but instead of picking those pictures of Rudy, I'm going to go over to this other photo or other folder, and I'm going to pick 3 pictures of 3 different dogs. So now what the network is trying to do is trying to make predictions for each one of those photos, average the answers together, it give me its best possible prediction. But I've made its life really hard because I've given it 3 different dogs that are not the same breed. So now it thinks it's a mixed breed, which is correct. But I can scroll down and you can start to see the layers underneath the neural network of how it works. And there are their predictions. So the water flowed through the network, came out with a probability, and that's the answer that I got back. Okay? That's it. That's how it works. That's an app that I just got from the store. I don't know what it's written in. Yeah. Yeah. So let's talk about what can go wrong. I mean, you would think, wow, this is an amazing way to solve just about any kind of problem. As long as I can throw a bunch of data at it and train it, it's going to give me the right answer. And you know what? It will give you the right answer a lot of the time. But let's imagine that we took that neural network that just had dogs in it, and we want to ask it to do one additional thing, like classify certain kinds of food. What could go wrong? Like dogs and food, very different categories, right? It should just work. So what's it going to classify? This is what a neural network scientist will call an edge case. An edge case happens when you are asked to predict something, or the network is asked to predict something that there was no training data for. Okay, so it's getting the answer wrong because it never saw the right data in the training set. That's what's an edge case. If you hear Elon and Tesla talking about self-driving is hard, they can get 95% of the way there. The last 5% is all edge cases. It's all the weird stuff that you never expect. Okay, because again, the neural network it doesn't have intuition. It can't guess. It can only do what it's been trained to do. Okay, so how far can we really take this, though? Like, it's just a set of pipes and a bunch of knobs, and we let it turn itself. Like, how far can we push this? Well, there is a very popular neural network you've probably heard of called Imagenet that was built to just recognize lots and lots of things, cars and trucks and planes and people and animals, very large data set. And remember how I said you can't really see into the hidden layers? Well, they eventually came up with a tool that lets you see inside of the hidden layers. I want to play a quick video for you that's on YouTube that talks about the Imagenet data set.
These synthetic images show that this neuron fires in response to a face and shoulder clears. We can also plot the images from the training set that activate this neuron the most, as well as pixels from this most responsible for activation, computed via the deconvolution technique. This feature responds to multiple faces in different locations. And by looking at the Newton, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces.
Interesting. Okay, so think about this for a second. Like, Imagenet had to have a classifier for human, for person. The neural network figured out all on its own that in order to accurately predict human, that it needed to recognize the shape of a face. And it, through all of its knobs, figured out how to detect the shape of a face. If you're thinking that sounds impossible, just wait. I'll address that in a second. Before I do, I want to show you one more video.
These synthetic images show that this not. Finally, here's another interesting one. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool because we never asked the network to look for wrinkles or text or faces. The only pages we provided were at the very last bit. So the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize.
Think about that. Like, it doesn't know how to read, doesn't know what the letters mean, but it recognized text, and it learned to recognize text because it had to figure out what a bookcase was. Like, that's mind-blowing to me. In fact, that's my next question. How is this even possible? Okay. Well, one of the first, like when I started teaching neural networks in campuses, one of the very first assignments that students were given was very simple handwriting recognition. Given the handwritten numbers 0 through 9, predict what the number was. Sounds super simple, right? Black and white images, only 10 things to figure out, 0 through 9. Train a neural network to do it. And this is that neural network. Now I'm just going to let this play for just a second. Hopefully. Okay, so let me pause there. You have your input layer. You have your 3 hidden layers. You have your output layer. For this very, very simple task of reading 10 handwritten characters, this network has 10,000 neurons in it, but 24.8 million synapses. Can you imagine trying to write this as handwritten lines of code? So many variables in, like, you'd have to handcraft shape detection. What do the lines mean? What do the angles mean? What does my handwriting look like versus your handwriting? All of that information are encoded into these neurons and how the information flows through that graph. It works because there are a massive number of these things in the network that have been tuned and tweaked slight amounts over days or weeks or even months to get the right answer every single time. And that's how it works. By the way, we're only seeing 2% of those 28 million synapses that are in the graph. Yeah. Yeah, so GPT goes way beyond here. Everything that I've talked about up to this point has been a classifier. I'm going to talk a little bit now about kind of taking it to the next level with data transformation. But GPT-3 goes way beyond. It's a new style of neural networking where all of your data set is, you can imagine it as encoded into ideas, right? So like, if there was an article about going to the store, there would be concepts in the neural network about what a store is and shopping and all that sort of thing. And so that is the level that the network is encoded at. So you could say, like, you could start writing a story and then it will figure out all the concepts that are in the thing that you wrote. And then it can find more concepts that are related to that concept and finish your story for you.
So, I mean, basically, there's a lot more around it than just neural nets. Obviously, some of it is neural nets, but there's a lot more built up around it.
There are different types of neural networks. There are different strategies of how we encode the data in the graph, the way that we represent the data in the graph. Like one of the most modern things that we're doing in neural networks is actually, it's kind of like an hourglass. We take all this information in, we compress it down as much as we can to its most basic essence, and then we can expand it back out to something else. And it's that act of compressing and expanding it back out that allows us to do some pretty crazy transformations. Like, if you've seen the NVIDIA thing where you like color by number and it turns it into a photo, that's part of that, taking this, compressing it, and then expanding it back out into a photo set. So, all right. So remember when I talked about labeling? The labeling was that it was a dog, it was a cat, it was whatever, okay? Well, the problem with this labeling part is that it's a huge labor issue. Like a human's got to sit in and do all this labeling. And so what if we could use machines to teach machines? Neat concept. This is what we call auto labeling. So I'll give you an example of how this is done. This is a paper published by the by a Microsoft team in Cambridge. It's called Synthetic Humans, or Synthetic Data with Digital Humans. And let me open this up. So let's say that you want to teach a system to do hand tracking, and you want to teach the system to do hand tracking reliably. Okay. Well, I'll come back to that in a little bit. Actually, did it show the? Yeah, it didn't show it there. If you want to do hand tracking reliably, we have a lot of problems to solve for. Though one of the most important ones to solve for is diversity. Not only diversity in people, like diversity in skin tone, body shape, arm size, hand size, but also diversity in outfits and accessories, okay? What we're trying to predict in hand tracking is the position of the joints. Now, we could do this in a classic way. Like, we could have video of this person walking through a space, and we could have a human being sit down and go click, 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 and label where each of the joints are. And that would take a very, very long time to label that data, okay? But what we can do instead is we can create a virtual hand. So this kind of looks like a basic 3D model, but imagine this is a very rich 3D model. It's not only the shape of a hand, but it also knows like where the bones are. It knows where each of the joints are within this virtual hand, okay? We can turn around and texture this virtual hand. We can light this virtual hand and get a fairly photorealistic version of the hand. So cool, we've got a synthetic hand. What do we do with it? Well, the next thing we do is we take, and I apologize, these pictures are really dark, but we take a human being, set them down in one of our mixed reality capture studios, and we capture them doing all kinds of things with their hands, different gestures and different arm motions and all this kind of stuff. Now, this capture that we do, we're using huge, very powerful computers to do these recordings. We have every frame. We've got unlimited computing power to track everything that's going on in this scene. So we know exactly how the thing moved. And what we end up with, you can kind of see all these little points here. It's like scanning. You have all these little kind of noisy points that are in 3D space that represent the shape of that human being. Again, because we're running in a data center somewhere, we've got unlimited computing power. So we can take that 3D hand that we had earlier, and we can figure out the best way to compress and squeeze and twist and turn that hand until it aligns on top of the recording correctly. Now that we've done that, we know where all those joints are in this recording. Okay, so now I've mapped raw recording to actual finger joints. On top of that, we can now use a very powerful rendering engine, and we can turn that hand into all different kinds of hands. So that one recording of that one person in the lab going through those gestures can be turned into all these skin tones. It can be turned into all of these different accessories. These are not photos, these are renders. It can be turned into all these different clothing items. We can even turn it into different backgrounds and different lighting conditions. And for every one of these photos, we know exactly where those joints are in that scene. So now we can take the photos and the joint information, pass it over to a neural network to learn, and then use that on a device in the real world. Okay, now, last thing, and I'll move on. It's kind of important to realize, because a lot of people don't, that different devices do hand tracking in different ways. HoloLens 2 does hand tracking with an IR camera. Other devices might use a color camera. You need to generate your data set in the same way that your device is going to see it. Okay, so if your device is going to use color camera, you're generating color images, so on and so forth. So you can see here, this looks like video, but it's not, because the arm is chopped off, and you can see the joint poses there in that data. Okay, so that's using machines to teach machines. Now, getting close to the end here, one really interesting point to convey is if there is ever bias in your neural network, it's your fault. It's not the network's fault, it's your fault. If there is bias in a neural network, the bias is in the training data. And I'll give you an example. I don't think Google does this anymore, but these are real screenshots from Google a while ago. And in English, we have the word like a defendant, a nurse. And when you translated that to German, you would get male defendant and female nurse. Same thing, going from in Turkish, there's this letter O, which is like it's gender neutral, but she is a cook, he is an engineer, she is a nurse, he is a doctor. Gender neutral translated to gender specific because of the data set that was being fed to the neural network. Okay, so this is a big part as we go forward, and we not only build simulations and we think about accessibility and simulations, but thinking about the neural networks that we build, making sure that we give it the right data so that it does the right thing. Okay, now, fun little thought experiment here at the end. Did anybody happen to notice something missing from that synthetic human training set? Something that might be maybe important to a certain industry or topical right now?
I'm not sure if it was an industry, but I kind of saw white hands to light skin hands, but didn't see any dark skin hands in there.
Okay, okay. There were some, but I guess I should say maybe not dark enough. What? Okay, holding a device. Missing finger. I didn't think about that. Very good. What about this? Okay. Now, I'm not saying HoloLens can't see a gloved hand. Remember, again, it's infrared, blue doesn't matter. But I'm saying, like, you have to think all the way through the use cases. Where's it going to be used? Who's going to use it? How's it going to be used? And you need to make sure that you build the right training set for that data. That's it. Any questions?
I have a question. So for, let's say you're doing object detection, say you have a model that's already trained. Is there any way currently that you can embed that into a Unity?
Yeah, and there are some companies that like provide libraries to do this, like PTC Vuforia does this. Like they have a Unity runtime, you can train a model and then you can import it into your Unity scene, it will detect it. Some of the Azure services, we have Azure Object Recognition as well. it turns out that the two different networks are a little bit tuned for different tasks. So Vuforia's network tends to be tuned for smaller objects like tools and saws and things. And Azure Object Recognition tends to be tuned for larger objects like vehicles. But yes, there are tools in order to do that already. No, they're both for on device, and they both can run offline. I'm more talking about the size of the object, and I won't get too much into how and why it works, but you can kind of think of like Vuforia caring more about the camera video feed, and Azure Object caring more about the shape detection and the network mesh that's in the world. So like we can detect a large car very well. Yep. I'm curious, was this helpful? Does this like bring anybody closer to understanding this? Yeah. Good, because this was like so foreign to me when I started trying to understand this stuff. I think you had your hand up first.
Yeah, so this is a little bit about how it works.
Oh, how do you do it? Yeah, I probably should have had some next steps there. Probably what I just said. Like if you're not a neural network person, like if you're not going to go handcraft these things yourself, find a library. Go grab Vuforia, go grab Azure Object Anchors, and like both of them are pretty easy to use. There's some pipeline that lets you like upload a 3D model that it's going to then generate a network from, and then that you take that network, put it on your device, and then the device will find it at runtime. And you don't have to go through like handcrafting your model or loading it in the Unity runtime. Just a second.
Are you saying that Azure trains the model, or Azure just does something on device?
So that's a great question. Think about it as like a transformation. Okay, remember when I was showing the digital humans and there was all this compute that was available to you in the data center that was doing like fitting of the model and prediction? Like that's a very costly, expensive operation. So you want to do that ahead of time, and you bake it down into a neural network model that runs very, very fast and doesn't require a lot of resources. So in both cases, whether it's PTC or it's Azure Object Anchors, you're using the cloud to go through this training part that requires a lot of resources, and you end up with something that's lightweight and can run on the device very quickly. Back in the back, you had your hand up.
Oh, I was, if you didn't already cover this, why you can't see into the black box and how we fix that?
That's getting beyond my understanding. Generally, again, it's the software that tunes all those knobs, so we haven't had a need to see inside of it. My understanding is that the videos that I showed you, they kind of like added shadow nodes on the network that were additional outputs that their visualizer could plug into. So it actually tweaked the network in order to get those outputs so that they could render it on the screen. Yes. With what? With Azure Spatial Anchors? Well, okay, because there's two different things that Microsoft provides. One's called Azure Object Anchors, which recognizes cars and in large pieces of equipment, and there's Azure Spatial Anchors, which recognizes places. So which one are you talking about? So we don't use neural networks in the same way. Well, so kind of. There's a lighter weight process going on that when you have a camera feed, like OpenCV can do this. You can point it at a space, and in that camera feed, it will say, "Oh, this area is interesting. There's a lot of detail here, and this area is interesting. There's a lot of detail here." Those are what we would call feature points. When you're creating a spatial anchor, you're basically creating an anchor that sits between feature points, and that's effectively what that is.
Pretty easy for I to recognize or figure out where it is in relation to something interesting.
Yep.
But then when you have like
right, because there's no feature points. Yep. I think you were next. Yeah.
Do you think that in the future we're going to have a point where we're going to be able to plug in like a neural, these kind of
systems that were like digital projects that recognizes dogs and cars, bikes and stuff like that? Or does that exist right now, or will we have a point down the road where is it ever like larger and larger library?
Yeah, those exist. Where I see kind of the shortcomings of the current approach is two things. One, the Unity tooling is not good. Okay, so you end up with like two different libraries that make it really easy, and the rest of it's kind of hard. And then two, the vast majority of these data sets are 2D. They're expecting a photo, and they're going to do something with the photo. And that's fine if all you're wanting to do on your AR headset is be told what's in front of you. But once you want to start locating that thing in space and interacting with it in space, then your training set needs to be in 3D as well.
We're a ways away from like aiming on our HoloLens 6 or whatever that looks at a scene and says, that's a car driving by, that's a bike over there, that's a bird in the sky.
Again, we can do some of that today, right? If you were to go to Azure Object Anchors, I think you can have up to 3 different types of things that it's recognizing. So I can have it recognize a couch and a car and a forklift, and it will find it. And it will find exactly where it is. And I can anchor content to it. And I can switch. I can say like, okay, I don't care about the forklift. Now I care about the fridge or whatever, right? But yeah, there's lots of stuff that can be done to improve that. There aren't like marketplaces of, I want to recognize the Sony whatever. There's no marketplace for that right now. You're going to train it yourself. Yeah. Yes.
So you do just like download what's the best way to?
Well, again, like if you're going down the TensorFlow path, for now, you're kind of going down a different path than an XR path. You're probably working with 2D data sets. Maybe you're working with 2D photos. Maybe you're working with 2D video. And for that stuff, honestly, I just go start grabbing Google Colab workbooks. If you can find it at a Google Colab workbook, you can basically click play. And that's how I've learned a ton of this stuff. But again, that's a deployment to solve a different type of problem, not a spatial problem. Yes.
I just wanted to share this because it did get brought up. I was trying to make AI play volleyball, and Unity has this thing called ML8.
Yeah.
Which is basically it uses TensorFlow, and I downloaded it last week, so I didn't get to mess around with it. But it sounds like it could do some stuff at least in.
Yeah. And what the ML agents are great at is you can think of an ML agent as trying to emulate the human. Like you demonstrate for it what you want it to do, and it will figure like, oh, you're not supposed to collide on the wall because the human never lets the car collide with the wall, which is also super fascinating stuff. Where you're going to have to be, well, I guess what I haven't seen yet is I haven't seen that applied to large scale open mixed reality, right? Because if I'm training a car to drive around a track, it's a very fixed set of rules with a fixed shape and a fixed world. Once you go outside that box and where your app, the canvas of your app is everything, like I'll be curious to see how much that can be applied, but I think it's phenomenal tech. Yeah, absolutely. Cool.
What are the current limitations? Like, I know a while ago I had every model in the world. What are the other limitations of this?
Yeah. So a general rule of thumb is that you use neural networks to solve a problem that is either unsolvable or extremely difficult to solve with classic programming, right? The thing that there's too much variability in the thing you're trying to recognize, or, like it would just take years to try to program it by hand. That's a good hint that you should be using a neural network. On the HoloLens, we run a runtime called WinML. Onyx is a format that's popular there. OpenCV can run there. You're running on a mobile class device, and you're always trading off between battery life and heat and the code that you're running on there, plus you're also generating a virtual world on there, right? So there are constraints that run there, but there's still a lot of stuff that's done there. A lot of very interesting things. You know, we have a product called Guides that teaches you how to or can walk you through the repair of a piece of equipment. And now it's built into the product where step one is walk into the room and let the headset identify the piece of equipment to be worked on. And that's a real shipping use case today. So yeah, I mean, you know, like the stuff is just limited by the constraints on the device, the resources on the device, but those are continuing to expand. So, all right, I'll stick around for a little bit afterwards, but I want to be respectful and cut off the recording. And thank you all for showing up.